Okay, good afternoon, everyone. Thank you all for joining us today for our weekly webinar series. Today, our featured topic is understanding and choosing an OTDR. My name is Jessica Petrohoy, and I'm the marketing coordinator at fiberoptic.com. Fiberoptic.com is a leading provider of fiber optic products, training, and rental equipment. We're pleased to present this topic to you today. So with us today to talk about understanding and choosing an OTDR is Christopher Labange. Chris is the president of the ITEL Group and fiberoptic.com. Today, Chris will be discussing the factors involved in understanding and choosing an OTDR and what features you need to consider before making the big purchase. And remember, our webinar series are recorded and available to you online at fiberoptic.com/webinar. And when Chris is finished, we'll take questions from the GoToWebinar question box at the bottom of your screen for a question and answer session. Thank you again for joining us today, and at this time I turn the presentation over to Chris.
Okay, thank you very much, Jessica. I appreciate the introduction. And to all of you out there, for the presentation of understanding an OTDR and choosing an OTDR, I think this is a very interesting topic. I think it's one that really can't be understated because some people believe that when you're purchasing an OTDR, it's just going to perform the same regardless of manufacturer, user, and distance, and a couple other factors. So we really want to help you making good decisions. And fiberoptic.com has been a leading distributor of fiber optic test and measurement equipment, i.e. OTDRs, for the past 15 years. So it's something we understand well, and hopefully can give you a little bit of insight into what might be the right option for you. So again, appreciate your attendance today. Let's get into it. Okay, for the agenda, 4 main topics that I'll try to address throughout the presentation is what do you need to test fiber? So if you're going to use an OTDR, that's certainly one of the mechanisms that you can use to test a fiber. Others are power meters, light sources, and this is all the physical layer testing procedures that we're talking about here. So what you will need to perform your test, what type of connectors will I be using? So whether they're SC as pictured in the screen here in the middle, you need to make sure you have the same connection when you're connecting to the OTDR, or at least your launch box. Really, it would be your launch box in this case, and we'll get into that a little bit more in detail. But what connectors do you have on the end of your fibers? The fiber under test is going to be an important thing. What features are most important when you're talking about your OTDR? So there'll be a couple key configurations or settings that we'll talk about that are really going to be important. And some of these are settings, some of these aren't. Some of these are characteristics of the test equipment. So some of the settings that we'll want to use, but then also when you're purchasing the OTDR, what wavelengths, what modules, things of that nature do you want to make sure you have, because they are not able to be modified in the field. Those are going to be set up and configured at the time of purchase. You want to make sure that you have those all correct. And then where will you get support? Are you looking for support from a field rep to come out and give you some training, or are you going to provide are you going to, really what I'm getting to here is how is the support coming? If you do purchase from a U.S. authorized rep, you're going to be able to get support here locally in the States. A lot of transactions are happening over eBay and other applications that are bringing in product from around the world. And some of those issues that you have is just with that support. Can you get the support you need? Can you get the training that you need if that's the case? So I think that's just something that needs to kind of be considered when you're making your final purchasing decisions. Not going to knock anybody for doing what's right for their business, but it's just something that needs to be considered. So these are some questions that I think you probably need to have answers to when you're going into making your OTDR purchase. What wavelengths will I need? So wavelengths are obviously going to be important. I'm not sure what level everybody is at on the webinar here. So just as a high-level overview, what we have is we have several wavelengths that are most commonly used in OTDR testing. Okay. there's two types of fiber out there. There's single mode and multi-mode fiber. Okay, so if you're working in an environment requiring single mode, you're probably looking at 1310 wavelength, and probably the second wavelength that you would want to test would be 1550 wavelength. If you're working on a multi-mode system, which would typically be a premise system inside a building, something like that, you're looking at about 850, it's actually 850 nanometers, and then 1300 nanometers would be your second wavelength. So as you'll see in each of those, I gave you at least two wavelengths for each kind of configuration. There are some other options that are out there that you'll want to take into consideration, and we'll get into a little bit more detail about what those might be later on in the presentation. But know that wavelength is going to be a huge differentiator, and certainly single mode and multi-mode would be the biggest deviation that we would have, and we want to make sure that we understood those, and then there'll be a couple flavors within each of those groups. What connector types are we using? So as I mentioned, we typically will have a connector that is sitting at the end of the fiber under test. So that fiber under test is really going to be the connector or the port at which we're going to make our physical connection. And there's a couple things to consider. One is, are you plugging the OTDR directly into the fiber? Hopefully the answer is no. We really don't want to do that. There's a couple reasons why, and again we'll get into that with damaging the front end of the connector, being able to see the first connector to make sure you have a effective connection and things of that nature. But you will need to know that if you don't have a launch box that has the appropriate connector and appropriate mating sleeve, then maybe you have to connect to it just to test continuity or get some sort of basic reading. But always be prepared, and make sure when you're leaving your main office, going out to the location of your test, make sure you have a launch box that has at least probably 1 kilometer if it's going to be a single mode unit, or at least 100 meters if it's going to be a multi-mode unit. But make sure you also have a set of adapters that are going to be able to convert from an SC to an ST or a Frank Charlie FC. Some other ones out there that you may come across are Biconic or SMA connectors, things of that nature. So make sure you have a variety of adapters and things of that nature, so that when you get out there, you're going to be covered and have the appropriate fiber connectivity to perform your test. So connector types, always important to know. What distances will you be testing? Obviously, the distance is going to be an important factor. There are lower end OTDRs that are perfectly acceptable and perform perfectly well in shorter distances, but once you get out to the field and you're trying to maybe test a 50, 60 kilometer span, depending on the amount of loss that is intrinsic in that span, your, let's just say, metro or fiber to the home type of OTDR might not have enough power to be able to make an accurate reading. So we'll talk about that a little bit more detail as well, with the power settings and what you need to get into, making sure that you have the appropriate unit for the distances. And then also, what type of tools are frequently used with OTDRs. So if you're going to go out and perform some sort of test, and one example might be the recently launched brake locator, which is kind of a let's just call it like a poor man's OTDR, and that was the OBL, I think it's called the 301A, launched by Precision Rated Optics, which we just sold a number of units to Cablevision recently. And it really came out of a function of usability and how the tech was going to use the unit. So as you see, the next item on the list here is PM, for basically stands for power meter. So on a power meter, do we need a power meter on this particular OTDR? Visual fault locator, and also a VIP, video inspection probe. So again, when we look at this, I look at the procedures in the process. So what the procedures are, and what we worked with training the technicians in the field are on, was the what is the first step that you would take in troubleshooting a fiber if you went out into the field? And I believe what we understood the first step would be was that they would use a power meter to see if power was coming through the line. So normally this could be a separate unit, but if you want to keep it all in one, it makes some sense. So the first step would be to unconnect the fiber from the port, plug it into the power meter, get a measurement to see if any kind of light was coming through. There should be an absolute amount of power that is expected to be coming through there. And if you don't see that, then you need to kind of start to go through a series of additional tests. One of those might be seeing whether there's any damage or breaks in the fiber. So step one was the power meter. Step two became the OTDR. So they had actually a single wavelength OTDR. That's why they call it a break locator, not an OTDR, because it was really using one wavelength, and really we like to consider two wavelengths whenever using OTDR so that we can detect macro bands and other things in there. But for a simple troubleshooting process, that we shot out a 1625 nanometer wavelength over that fiber to see if there was a break down the span, some distance. If that came back and didn't show any additional problems, what the next step was, it was to look at a VFL, and the VFL would be put on the end connector there just to see if the connector was broken anywhere in the NID right at the end there, right before it came out of the connector. And if it was broken, the VFL would glow and highlight any kind of damage. So that would be step three. Step four would be VIP, which is the video inspection probe. So we would then, if there was no damage there, we would look at the end of the connector end face to see if there was any kind of damage to the end of the connector end face. So these types of tools all typically able to be purchased separately, but depending on what you're trying to do, and if you have a uniform process and procedures that your technicians are supposed to follow, they can work very well together and also be included all in one unit to perform an extremely efficiently together and also handle the requirements that are needed. So those are just some options. Again, that's an example of why you might want to see some of these other features included. Then again, the support issue. If you have problems in the field, where are you going to get support? Do you have local sales reps who can come out and teach you how to use the unit? I think that's incredibly important component of it. Otherwise, I think probably some of the overseas manufacturers would probably dominate the market right now because of price, but they just don't have that local support to help some of the customers work through issues, get warranties, problems, getting it fixed. Calibration is also another thing when you talk about support is, a lot of these pieces of equipment need to be calibrated every year. So if you're looking at a 1-year calibration, and you have to ship it overseas to get calibrated every year, then that's going to be a huge cost and probably not worth the hassle. Anything you would save, you'd probably lose in the transportation and extra fees associated with the calibration. So all very good things to take into consideration and make sure you have answers to when you're evaluating your product. So what will you need to test? As we talked about kind of briefly as the first item in there, what are the wavelengths that I'll need? Well, what will I need to be testing? Back to the idea here of single mode versus multi-mode. So as I mentioned previously, multi-mode, which is going to be our premise type applications, typically we're going to see 850 nanometers and 1300 nanometers. Again, we're looking at the two wavelengths here because what we're trying to see is the one of these wavelengths will be the wavelength that we will operate under, right? So we'll need to make sure that if we're operating at 850, we want to know what is the fiber look like, how clean is the fiber at that particular wavelength. So we'll want to make sure we use that as one of the measurements. But we also want to use this second wavelength as a way of creating a reference for a macro bend. So one of the big problems we have with fiber is bending of fiber. We get loss or attenuation, okay? Normally, the higher the wavelength, the better it will perform with fusion splice loss and things of that nature. But it's inversely related when it comes to bending. So the higher the wavelength, actually the more attenuation we'll get when you bend it. So with the 850, we'll be able to get a pretty clear reference of what the fiber looks like at 850. But if we see a certain location on that fiber, test, or that OTDR shot, that trace, where the 1300 nanometer wavelength actually has a higher drop off or a higher amount of loss at a particular event than at the 850, well, then we actually know we have a macro band at that in that location, and that's something that we'll probably want to clean up. So that's why we'll say we'll need 850 and 1300. So always recommending those two wavelengths. Standard single mode uses, as I said, 1310, 1550. But as we'll see here, where we get into a little bit more detail than I did in the previous slide, is every now and then the standard single mode starts to get a little bit more complicated, and we'll see certain circumstances where we've added additional wavelengths that may not have been standard, let's say 10, 15 years ago. So the first example of that will be the fiber to the home, FTTX application, where we'll sometimes see this 1490 wavelength come into play. And what that 1490 is actually the signal, the transport signal for the internet as it comes down from the head end. Okay, so our Ethernet traffic is going to come down to our NID at that 1490. Now from the house, what we're typically going to do is shoot up towards the head end. Any kind of information we would need to send back, we will transmit at that 1310 nanometer wavelength. So what we're trying to illustrate, here is you got the 1490 coming down, you got the 1310 going over back up the same fiber. So those two different wavelengths allow us to use the same fiber and transmit data in two directions. And then the 1550 nanometer wavelength here is what is reserved for what's called our RF signal. So for our television signal, a lot of those original television signals came with RF, so it's RF over fiber, and those were transmitted at this 1550 nanometer wavelength. So if you have a fiber to the home where it's using RF over fiber, then you would use that 1550. If it's IPTV, then you might actually not need that 1550 wavelength, and you might just be operating at 1310, 1490. So just something to take into consideration if you've got a fiber to the home application. Do you need to consider that 1490? Then DWDM, dense wavelength division multiplexing. What we're doing here is we're looking at the range, within the optical spectrum, where we can transmit multiple signals, kind of like we did with the 1310, 1490, 1550, all on the same fiber, but at different frequencies. They won't interfere. We have the same ability to do this at 1550, 1551, 1552, 1553. Now the spacing will be different, but it just is an example. We can separate these very down to like 0.2 nanometer in difference. So in that scenario, a lot of times what we're looking for is that 1550 wavelength, and because of the distances of a lot of those, the 1310 has too much loss that we typically have to bump up to like a 1625 nanometer wavelength to get the distances. So this is potentially, again, a DWDM system might be a core, core backbone for AT&T, Verizon, someone like that, where they need to get a lot of telephone calls, data, transmissions and all that stuff over one single fiber. They've got it all spaced out over very small dense wavelength division multiplexing spacing, and you want to be able to jump into that 1625 to test those fibers while they're performing at the 1550 wavelength, or potentially, because the 1625 nanometer wavelength is actually pretty close to the top end of where the DWDM operating range is, we're starting to see customers, specifically the cable television customers, Time Warner and others, just came out and requested a quad OTDR with 1310, 1550, 1625, and then a 1650 nanometer filtered wavelength. So what that is on that 1650 wavelength, they want us to actually put a filter in the front of that to filter out anything other than the 1650 wavelength, so that we can test the fibers while they're in operation and not interfere with any signaling and things of that nature. And because we can get so close to that range, at the 1625, we want to put a little bit more cushion or spacing between the upper end of the DWDM spectrum and the 1625. We bumped that up to 1650, and that's something that we're seeing a little bit more of nowadays, is that 1650. So live fiber testing, do I need that? It's a very, very big question, because again, that's not something that can be changed after the fact. You need to put a filter on that port to make sure you're taking the transmission that could be shooting down directly into your OTDR and filter that out, so that you don't damage the receiver. Because if you know about OTDR technology, we're sending a light down a fiber and looking at very, 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 very small reflections on microscopic particles in the fiber. So it's very, very highly sensitive and highly tuned. If someone was sending a signal directly down the fiber towards us, their power is so strong that it'll actually burn out the receiver. So we got to make sure that we're filtering out power that is not the power that we're trying to measure. So if you want live fiber testing, you need to make sure you talk to your sales rep about that and make sure you get that put in there correctly. Or do we need all wavelengths, a quad? That's what I was telling you about earlier. Typically, we're not going to see too many more than these 4. Now, there is some CWDM, that have 4 wavelengths or 8 wavelengths on an OTDR. There's even tunable OTRs that are coming out, which are a little bit higher in cost. But a quad, when we talk about quad, we're really talking about an OTDR that has 4 wavelengths pre-configured on it. So that's just something that you might hear in kind of the terms when discussing things with kind of sales reps. So how does an OTDR measure distance? Is one of the things I just kind of talked about briefly, and it's incredibly important to understand, so that as you're kind of going through and making some of these decisions, you know what to look for. So an OTDR is basically going to send a pulse of light down the fiber, and like I said, look for very microscopic reflections off of the intrinsic particles inherent in the fiber. So to measure, that's how it measures the loss and the distance. But also, if it's looking for these reflections, to measure the distance, it needs to know a couple other factors. One is the speed of light. So what we're talking about here is we're talking about sending light down the fiber in one direction and looking for reflections back. So we're really looking at a time, right? We send something out, it reflects off of something and comes back. So if we take half of the amount of time that it took to get back to the receiver, that's about the amount of time it took to get out to that endpoint, right? So if we know the speed of light and then divide that the light is traveling and divide it in half, that'll give us a good indication of our distance. So it's one of the calculations that we use, for the OTDR. And then the time it took for the light to travel down the fiber and return is the elapsed time, and that'll also, be an important, a factor along with the test pulse width. So it's not necessarily the speed of light that's needed, but it's typically what's called the index of refraction of the glass. So the IOR of the glass, which is going to, when we set that on the OTDR, and we want to make sure it is something we can set on the OTDR, when we set that on the OTDR, we're saying the speed of light through a vacuum, void of any air or anything like that, vacuum, empty space, is known. But it travels differently through air, water, glass, all these things. So depending on the type of glass we're going to use, we're going to make sure we use the appropriate index of refraction setting, so that we give the OTDR the correct speed at which it's traveling. So when it does lop that time in half, it has an accurate measurement of the distance and how far that fiber got before it was reflected back to, or how far the light got before it was reflected back. So that'll let us know the distance to that particular fault. So that's, that brings in a little bit more kind of high-level concepts of how OTDR is used. But like I said, you need to know that, and you need to know how the IOR comes into play there. Typical OTDR traces, what you're going to see when you're looking at a trace. Here's an example of what you would see. Not a big fan of this particular trace because it doesn't depict something that I really think every OTDR trace should depict. And I'm not sure why it advanced there. Hold on one second for me. Let's go back a slide. I don't know if it's timed or what, maybe mistakenly timed. We're looking at the launch, and then we're looking at the reflective event. So one of the things that I was saying is we typically always want to use a launch box. So what I would like to see on this OTDR trace is the launch, which is correct, and then we call this second spike a reflective event. Well, that's completely accurate. It is a reflective event, therefore we see that, typical spike that we would want to see at a reflective event. But what I'm really thinking of here too is we should really call this area between the launch and this first reflective event, I would like to see it depicted as the launch box or the pulse suppressor box. This would typically be a 1 kilometer length of fiber that we would use to kind of get the OTDR in its optimal calibration range. I always use the example of a flashlight pointed in somebody's eye. If we're talking about optics and I take a flashlight and I point it right in somebody's eye, your eyes are flooded with light and information, and we really can't see beyond the flashlight that's pointed at us. But if I take that flashlight and I move it to the far end of a football field 100 meters away, 100 yards away, I can see that light. I can kind of look at that light and I can see past that because I haven't flooded my my eyes with the light. So what we are doing with the launch box is essentially similar to that. If we launch right into the first connector of the fiber under test, I really don't get a very accurate measurement for the first couple 100 meters of that fiber, and I certainly don't get a very good measurement of that first connector. So by putting that launch box in place, what I get is I get to back that fiber up 100 meters if it was multi-mode, or maybe 1 kilometer if it's single mode. I back that up and I'm able to get a more accurate reading of that first connector. And that's incredibly important because if that first connector is damaged and we have this huge drop off of launch, at launch, which is fairly typical, we're really not getting a very good reading, and we're not really being able to identify that there's a problem with that connector the same way we would if we connected to a launch box, at the end, and then can get a more accurate reading of that. Completely agree with the reflective event call here. So the reflective event could be a couple things. It could be a connector, but we don't call it a connector because we don't see it. We can't necessarily be 100% certain it's a connector. Potentially it's a mechanical splice. Maybe it's a little crack in the fiber or something like that. Most of the time I would say it's probably a connector, but we like to refer to them as reflective events until we're sure and want to completely confirm that that is a connector in that particular location. Other things that we see on here is what's called a non-reflective event. So the non-reflective event is really a bend or maybe a bad splice in the fiber. We're not sure. Not by looking at one wavelength, which again we have here. Where I'd like to see this maybe having two wavelengths in here, so two traces kind of overlapping each other, because that's where we really get to see the 1310 compared to the 1550 wavelength, or the 850 compared to the 1300 wavelength, and be able to determine this non-reflective event. Is that a bad splice or is that a macro bend? Based on the information here, I really can't tell you until I had a little bit more information to be able to diagnose that, and that would be that second trace file. And then the end event. Typically the end event is going to be a very, very highly reflective event because there's the fiber or the light is actually leaving the fiber and hitting air, which creates a huge reflective event. So we have a very high spike there, followed by a very large drop, and then the noise floor. So these are all accurate depictions of events that we would potentially see on an OTDR trace, but I think that there's always a few other things that could be added to here and are probably more indicative of what we would see if we were looking at a trace on a true OTDR versus just kind of a graphical representation. So those are things to look at. And when we're talking about the OTDR and selecting it, the accuracy at which these OTDRs can read these reflective events and how much reflection is coming off these events is a huge factor. Okay. So again, looking a little bit more at the multi-mode environment, what we have depicted here is again an office environment, because typically the multi-mode systems are going to operate in this 850, 1300 nanometer wavelength. They're going to be between floors or between buildings. They're going to be indoors, very short distance applications, horizontal links, between buildings or between floors. So it's not going to be a very long run. It's going to be a shorter run. So your dynamic range can be a little bit lower. You don't need like a 40 dB OTDR for multimode. You'll never shoot that far. You'll never have multimode that travels that far because from the industry specifications, it's really meant to be at a maximum of like 2 kilometers, that you would have, and even at that, it's really expecting like 10 megabits per second transmission rate at that. So you're looking at maybe fire suppression systems, signaling systems, for signs or something like that. Very, very low bandwidth applications that you'd be looking at. So. And the multi-mode core, as we show you over here, is about 62.5. It's about half the diameter of the fiber, which is 125. So that's showing the cladding and the core size relative to each other on a multi-mode. So when you're looking at your system, you really can't use a multi-mode OTDR and mate it up against a single mode OTDR because the core sizes won't align, and therefore you won't get accurate measurements. So you need to make sure you know what you're looking for at the time that the units are purchased. Single mode, to kind of represent the fact that single mode is going to be their long haul applications. Seeing much more single mode applications in the premise environments as well, between buildings and even on campus now. For a long time that wasn't the case just because the cost of single mode was so much more expensive. The LEDs that we use to launch into a multi-mode fiber were a lot less expensive than the single mode transmitters and receivers. So there was some advantage and cost savings on the short haul to use multi-mode. But we're seeing, as more and more mass manufacturing occurs, we're seeing more and more single mode being applied into all aspects, just so you don't have to worry about upgrading, because there's a lot of environments, especially campus environments that we've worked on with where they used to use multi-mode as their network, but then over buildings when they were trying to just do 10 meg between buildings, but now when they're trying to do 10 gig between buildings or 100 gig, they needed to move to single mode, and they moved their fire suppression and some of their security systems onto that old multi-mode fiber. Outside plan, WAN, and long haul applications, again, all things that I've kind of alluded to here already. The fiber to the home wavelengths, as we talked about, previously, we've got the 1310 nanometer used for the return path, 1490 for your voice and data downstream, as I said, and then the 1550 for that downstream video. So those are just another way of kind of highlighting those comments that I already made earlier about why we would need those particular wavelengths for fiber to the home and how each one of those is used kind of currently. So, and here's an example of what we're talking about with the DWDM systems. So the graph here, which is important, shows this between 1350 and about 1400. There's this huge black spike in the loss of fiber attenuation curve. So that's why for a long time, if you look at the O band, which is the lower band on the optical spectrum, the O band 1310 was the lowest point, or the lowest amount of fiber attenuation on that side of that water peak. That was created by the water hydrogen molecules that were intrinsic in the fiber throughout the manufacturing process. And then 1550 was actually the low point on the opposite side of that water peak. So we use 1310 and we use 1550. because we got the best distance and loss performance at those two wavelengths. But now, as you see, if we're moving up into 16-channel DWDM or 8-channel DWDM, and we're using the C band and L band, if we're only using the C band, then we could get into doing our fiber monitoring on the 1625 L band. But as we've started to see, as you see that second larger circle for the 18 and DWD or 16 and DWDM channels, we're getting up into the 1600 L band wavelengths that we're using to transmit signal over. So that's where we're looking to potentially bump up to that U band and use that 1650 nanometer to get that appropriate spacing. So the typical DWDM spacing, as you see, here is 0.8 nanometer is what we can get to for for our 40 channel 100 gigahertz modulation there, and that's something that is incredibly advantageous when you got companies that are trying to put like 16 terabits of data over one singular fiber. Really, for the most part, we're looking at systems that are trying to do 100 meg. And now they're actually got systems that are trying to do 100 gig, trying to do 400 gig. But even the ones that are doing 100 gig right now, a lot of them are multiplexing 10 gig channels to kind of get up to the 100 gig data rates. So if you're looking to do 16 terabits and you're trying to get all that bandwidth on one single fiber, you've got to be able to get up to those 40 channels with very, very tight spacing and very, very high bandwidths. So the crosstalk and some of the other stuff that is potential hazards there are all things that need to be considered when you're putting that kind of traffic on there. But make sure that you're looking at those bandwidths. You're making sure you're understanding if you want to do live monitoring of fibers that you're up. If you're doing DWDM, I really recommend you bump up to the 1650. Even though you get a little less loss performance, there, because you start to tick up, it's still relatively effective, measurement, and you can still get pretty good distance, but you also get a pretty nice separation between the other wavelengths that we're operating under. One of the other factors is the ferrule. So when you're looking at your OTDR, you need to understand and make sure that the ferrule that you're connecting against is appropriately polished. So in this picture here, we have a hybrid jumper, which is taking it from an SC APC, which is green, to an SC UPC, which is blue. And the difference is that APC connector actually is an angled ferrule, which is an 8-degree angle to reduce back reflections on systems that are like fiber home systems that are maybe using 1550 for their RF signal, their video signal, and that has a lot of reflections that come back, and the reflections cause a lot of bit error rate problems at the 1550 wavelengths if there's a lot of reflections in the system. So what they do is they put that little APC on there, and that minimizes the amount of reflections that are occurring. Very nice feature, but you can't plug a blue connector against a green port and get that to mate correctly. You're not making a true contact at that point, so you're not going to get an accurate test if you haven't made sure you're mating appropriately. So make sure you have your hybrid patch cables in your box. Make sure that let's say your launch box is APC. Well, if you're mating up against a UPC, you're going to need another jumper to kind of convert that over to make a good connection against the port that you're mating up against. So know your angle, know your connector, and make sure that if you're using any kind of APCs, you have the appropriate APC polish on your OTDR. The distance, well, when we talk about distance, everybody likes to say, well, I need an OTDR that'll shoot 100 kilometers. Well, it's not like the OTDRs are meant to shoot a certain amount. Again, I use the idea from that everybody hopefully understands is I use headlights in the fog. Okay, so if you tell me you want headlights that can shoot 5 kilometers or 5 miles down the road, Sure, on a crystal clear night, you got lights that'll shoot, 5 kilometers down the road. But I say if it's foggy and you're in, a real low-lying damp area and the visibility is low. I mean, I've been out where sometimes you can't see 100 yards in front of you. So the power of the light did not change. The amount of refraction and reflections that are occurring based on particles that the light is trying to travel past has increased, and that affects the distance. Well, the same is true with an OTDR. The dynamic range is really the amount of power that the OTDR has in it. But if you are operating in on a fiber that is very, very dirty, has a lot of bad connectors in it and high loss because of bad splices, you're only able to go as far as the amount of power that you have left. So let's say we're launching, we've got 32 dB, we launch, we come out of the launch cable and we have negative 0.75 dB loss. Well, then you have to take that out of the equation. And then you go another couple meters and you've got a bad fusion splice that's maybe 3 dB. Well, then you have to take that out of the equation. So each event that you run into is absorbing power, and that's going to affect your total distance. So that's just something you need to take into consideration. Ask about a dynamic range, know the power, but then also know typically what you're trying to measure so that you know if you're going to be able to get that full distance. Measurement range is really one of the things that you need to kind of take into consideration. So what we're trying to show here is you need to subtract about 8 dB from the dynamic range to make sure that you're able to accurately measure the fiber under test, because your noise floor is going to come into play, and I'll show you that on the next screen. But you take that dynamic range and you have to probably subtract about 8 dB to make sure that you've got enough separation between your noise floor and any kind of events that are trying to be measured. So that's an important factor. So again, you need to make sure you select an OTDR with the module that has the dynamic range and wavelengths that you're looking for. So when you're looking, let's just say we were trying to do a 100-kilometer span, right? If we're trying to do a 100-kilometer span, if we're measuring at 1310 nanometers, we're typically going to have about 0.35 dB per kilometer loss intrinsic in the fiber. That means no splicing, no connectors, no nothing. Just as we're going down the fiber, the light is being absorbed in the particles at about 0.35 dB per kilometer. Okay, so if that's the case, and then we have other factors that come into play like splices, connectors, things of that nature, then we were really going to impede the amount of how far we're able to shoot. But if we're able to go, what did I say with 13? 0.35. We're going to have, if we try to go 0.35 and we're trying to do 100 kilometers, that's basically 35 dB of total range that we would need right there. So if we take the 8 dB kind of overhead that we want to look at here, we're really looking at needing about a 43 dB OTDR to be able to accurately measure that kind of distance. So that's a high-powered OTDR, 43 dB. You can get 40, you can get even up to 50. They're very expensive, but you can get it. So one of the other things that we could do here is instead of measuring at 1310, we can measure at 1550. Okay, so if we measure at 1550, we have about a 0.22 dB per kilometer loss. So again, if we were to measure the same 100-kilometer span and we have 0.22, that's only going to absorb about 22 dB of power over that length. So if we add the 8 dB of overhead into there, we're really only needing about a 30 dB OTDR, which is a very, very comfortable range. Typically we're not even going to sell OTDRs that come in below like 34, 32 nowadays. So you just need to make sure that you're looking at, if you're going to measure above, like I'd say 60, 70 kilometers, I really recommend an OTDR which is maybe 1550 and 1625, because you're going to get that extra distance at a lower power output. So that's just something that you need to kind of work. And again, give us a call, talk to us, tell us what you're trying to accomplish, and we'll be able to walk you through that. But in this kind of picture here, this is what we're trying to illustrate is this dynamic range. So between the two blue lines here, the one on the top where the arrow is, that comes in at about 26, 27 dB, runs all the way across, all the way down to the bottom, which is to 0. That's the full dynamic range of an OTDR. And the difference between the dynamic range and what we talked about with our measurement range here is really going to be the area which we see how the noise comes in. It starts to get kind of noisy over here at around 8 dB. Well, at around 8 dB, anything beyond that, we're really not getting an accurate, clear measurement of what the event looks like because the noise is really masking a lot of that. So what we're trying to illustrate here is the measurement range is the difference between the dynamic range and about that 8 dB of power. 8 dBm, I guess, if you want to say, is a power measurement, or 8 dB loss. So you need to take that into consideration when you're coming up with some of your numbers, because you've got this launch, this green area on the far left. You've got that launch. It's going to drop down, a half a dB or so for that launch, and then you've got from that point at which it enters the fiber down to about 8 dBm as your measurement range. And then some of the other features that I talked about already, built-in power meters, visual fault locators, inspection probes, IOLM or some sort of trace, analysis, configure software, Wi-Fi connectivity, and cloud-based storage are just some of the other, factors that we'll want to consider. And in here, the built-in power meter, most testing today calls for a power meter and light source to be used in addition to an OTDR. An OTDR is great, but there's really only one true method of measuring loss, and that's core power. So inserting light on one side and receiving it on the other. Because other things can be manipulated with settings, incorrect settings, and things of that nature. So, it probably makes sense to just get a built-in power meter on your OTDR. What I like about it is it allows you to save the test results of the power meter setting right on the same device as the OTDR, so that you have all your record keeping in one place. We test thousands of fibers, a year, all across the country in a very high level test called fiber characterization. And it's always fantastic to have all that measurement on one unit. So the power meters and light sources can be built into the OTDR to reduce the number of items carried. The way that they integrate the light source typically is going to be the same source as the OTDR source. Okay, an OTDR source is pulsing to get measurements back and forth. It pulses at a certain frequency to allow it to get more clarity over the fiber. Now, when it goes into laser light source mode to be worked with the power meter, it's going into a steady hold pattern. It's just turning it on and holding at a consistent power setting, and it doesn't flash at all, so there's no frequency. So it becomes a stable light source at that time. So that works out and allows you to leverage some existing equipment that you have to get an accurate measurement. So very, very possible to integrate a power meter and light source into your OTDR. Visual fault locator, probably one of the best tools you can get. This one, if you got as a separate standalone tool, I'm actually very, very comfortable with that because there's just so much you can do with it. And we have very small pen style VFLs that I really recommend. They're great. Every technician who's doing fiber should really use that. But if you're going to have an OTDR, might as well get that added to the equation as well, so that you can. The only reason I say it doesn't have to be part of it is because it really doesn't take any measurements. You don't save any results with a VFL, but certainly does a number of things for you. Some of those things identify bends. So that's kind of the second picture from left to right on the top there. If you bend the fiber, you're going to be able to see that fiber glow. Locate breaks. Certainly going to do that for you. Detect any kind of breaks in the fiber where it'll glow. Verify continuity. What you're looking for there with the verifying continuity is you're looking to go at the far end of the fiber. Do you see the light coming out of the far end, which you should if there were no breaks. So you like tone for copper. VFL works the same way to see if you've got continuity on it. End-to-end identification. Now, a lot of times what will happen is you'll have a splice that happens somewhere mid-span. So you got a 1 kilometer span, and somewhere in between, blue was spliced to black because it was dark at night and nobody could tell the difference, so it was misspliced. So when you put it on the blue on one side, it comes out the black on the other. That's a very good end-to-end identifier. And building it in means fewer items to carry. Some of the other things that I also identify, it detects scratches, I think, on a connector. So one of the things that I've been able to do is put it on the back of a connector, and don't point it at your eye, but you point it up in the air, straight up into the air. And if you look at it at a 90-degree angle, like from the side, if there's a little star at the top of your ferrule, there's dirt or debris there. If you wipe that clean, you shouldn't see any kind of star or reflection right at that point. There's a way of, if I didn't have a microscope, I've actually been able to clean connectors or tell whether they were dirty by actually looking at it and detecting scratches or debris on the end of the connector. So just very, very good ways of using a visual fault locator. So if you can get it built onto the OTDR, why not? Video inspection probes. Here's an example of a Fluke handheld inspection scope that stands alone. But again, if you can build that into the OTDR, what you get is this nice depiction on the OTDR of what that fiber end face would look like, and that's a good indication there that you've got a very clean fiber. There's no scratches, there's no debris, there's nothing on that connector end face which would be impeding the performance and cause any kind of result problems. Certainly an OTDR that is dirty will give you bad results. It will mess with the trace. So if you go out and shoot it and it's dirty, you're bad data in, bad data out. It's not going to be accurate. So always make sure before you connect your OTDR to any device, you always want to make sure that you've inspected the connector end face so that you're not going to damage the connections that you're making and cause permanent damage. Link view system or other IOLM or smart OTDR type systems. So there's 3 out there that I would recommend, and I do think it's worth buying OTDRs that have these. And this is again a separation between probably Precision Rated Optics, Expo, Viavi, and some of the cheap OTDRs that you're going to buy overseas is this link view technology. Where you can actually get a graphical representation of what's viewed in the field. Viewed in the trace. I absolutely require that my guys have access to the OTDR trace because all of these systems make errors. It's not 100%. It's not foolproof. Don't go buy the link view system. Great reference. Get a quick straight line map of what you think is going on. But there's very, very frequently you get APC connectors misrepresented as bends or splice events because the reflections are so low because of that angled polish. So it'll put a connector, or it'll put a splice somewhere that it really is a connector. And that actually can confuse people because it's guessing at what it thinks it is. And if you can't go back and look at the original OTDR trace, you'll actually wind up documenting your spans and that could cause all kinds of other problems. But do like this for the novice who doesn't know what they're looking at. And again, this was the part of this link view system as part of that OBL or poor man's OTDR that was delivered to Cablevision from the Pro solution. Where they had that special process that they wanted to kind of go through. So again, first it was the power meter reading. Second was throw it on link view to see if it saw anything. If it did, they were supposed to go to the OTDR view to kind of double check the analysis that came up and then go through those additional sequences of troubleshooting events. So good software. Recommend one of these solutions for sure. Does the client have any requirements, saying that they want Smart View or Link View or IOLM or anything like those that goes along those? So you might want to make sure that your customer doesn't have any requirement for those. Wi-Fi connectivity. Becoming an increasingly requested feature. Again, not something a lot of the overseas OTDRs have, but if you can get it, I would, because it makes life a little bit easier. One of the things that we're offering at fiberoptic.com is this management of OTDR traces. So what you can actually do from your OTDR is upload it via the Fiber Connect software right into a centralized database that'll allow you to store and document your network. So, if you can get that Wi-Fi connectability, that's a great feature, and I would certainly recommend it. Also, if you can't, one of the things we're showing here is, you can also plug into a tablet that has Wi-Fi at least, and use that tablet as a way of connecting back into the system and uploading your traces. Because what typically happens is somebody goes out, shoots it, gets saved as a PDF, and then never used again. But if you put it as part of your network documentation platform like Fiberbase, then it's always there, and it's in the system you're constantly using, so you can kind of identify any kind of degradation over time or any issues that might eventually occur. That if it was just a PDF somewhere and you ignored it, you really wouldn't be keeping on top of proactively identifying what might be causing some degradation. So. Cloud-based solution, again, here's kind of a picture. Again, three kind of players, Fiberbase and Fiber Connect from Precision Rated Optics. Exfo has Exfo Connect, and Viavi has StrataSync. Again, the solution here is you've got this gentleman in the field. He's got this tablet. With this tablet, he's selecting his project and then selecting the files and uploading the files right into a project so that it's stored and managed, and the project managers can keep track of that. And then over time, with Fiberbase Connect versus Exfo Connect or StrataSync, the Fiberbase Connect is actually connected to a map type of application, which if you put your two endpoints into the map, like Google Maps or something like that, you can see those two locations. Then it'll draw a straight line between your two, your starting point and your end point. But over time, if you actually knew where the path of that fiber went, you could actually drag that along street routes and get the exact location of any kind of bends or something like that. So starts off with uploading it to a project. The project will have two endpoints. It'll be straight line, for immediately, but then you can go back into the full Fiberbase application, not through Fiberbase Connect, but through full Fiberbase application, and you can actually draw the conduit pass and then drop and direct the fibers to follow the path that it actually does follow in the field, which makes, again, troubleshooting in the future much easier, because an OTDR will show you where loss occurs, but if that's not mapped to a physical GPS coordinate, all you have is distance, and you're going to have to kind of drive that distance until you can figure out where that is. So cloud storage is definitely extra cost, but probably make sure you have platforms that are worth investing in, because in next couple of years this is where it's going. Support. What support will you need? Obviously, that's, like I said, training. What kind of training do you require? We're able to train customers on Exfo, Viavi, AFL, Precision Rated Optics, and Ritsu. So any kind of OTDR support that you need, we can certainly help you out with. That's not a problem there. We can provide maintenance, calibration. We can do all kinds of support there. We can come out and do field training if needed. So from a support standpoint, I think we can pretty much cover you, but you might also want some manufacturer support and warranties and things of that nature that you may want to look into. Certainly makes sense to probably go with a 3-year warranty. Again, we do a lot of testing. I'd spend the money for the extra warranty. We do a lot of testing. These things are sometimes 10 feet in the air at the top of a rack where we're climbing up a ladder, and this thing gets dropped off there, and things happen. So if you can get a warranty that'll support you for 3 years, I think that probably makes some sense as well. Again, a word about the launch boxes. Certainly when looking at your options, make sure you take the launch box into consideration. Again, this will allow you to analyze that first connector, this is an example. On the bottom is a launch box, a launch bag by Precision Rated Optics, where you can kind of get your leads, and they come right out of the bag, and it works kind of well. You can put your cleaning supplies in there. They also have a hardened launch box, which is in a Pelican case, which works well too. But we're seeing more and more interest in this bag approach because it can be used to store fiber, cleaning supplies, and things of that nature. Some of the problems with the Pelican case is if the guys aren't careful, they'll actually crimp down on that 3 millimeter zip cord there and crack the fiber under there, and then they'll have to send it back for repair. So that's just one of the downsides to that versus the zipper. Yeah, you might start to zip it up, but you're not going to really crack the fiber within there. So that bag style is really nice, and we're seeing good feedback on that. But definitely, and there's actually the OBL I was telling you about in the picture here, OBL 301. That's that single wavelength brake locator, but has multiple functions kind of built into it. Really, really good price. Great entry-level OTDR / brake locator. But also, even a brake locator, definitely recommend the OTDR launch box to be used with that to make sure that you're getting clear depiction of what's going on in the field on that first connector. Otherwise, it's really hard to troubleshoot these things when you don't have a launch box, because if there's dirt and debris on that first connector, we can't measure it. You start to assume it's equipment failures. You start to make all these assumptions that just maybe aren't true. Illustration of particle migration. So this is one of the things that we're talking about. Why use a launch box? Why use cleaning supplies? Always, 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 always inspect your connector, clean your connector, and use a launch box. Each time the connectors are mated, you'll see the particles move around the core, and causing them to get air gaps between the fibers, and dirt and debris and particles smashed and damage the end ferrule. So this is showing the first one. We make a connection, we smashed against that, we took big particles after the first mate and broke them up, shattered them, spread them further across the ferrule, and then got them to kind of rest on the connector end face. But we got our measurement. It wasn't great. We're looking at it. We forgot to clean again, so we're going to mate up again, and then the second time, boom, smash it again. So this is now our second mating. We've broken up those particles again. Started to probably do some permanent damage to the connector there. And now we're probably going to have a very difficult time cleaning this up and getting an accurate measurement. Making it again, you start to see as that fiber started to leave, we actually started to depict a little bit of a fracture in the core there. Now we've got glass and shards and dirt and debris all over the center of the core where transmission occurs, and we've got probably fractured core. Which is really where the light travels and is not going to allow us to create accurate measurements. So as you can see, then we go and we make this fourth measurement. We've got all this particle in there, and these particles are actually holding the fibers apart from each other, not allowing us to get a clean mating, and probably going to get a very poor launch, and therefore bad results of our tests on this. So definitely make sure you clean, and make sure you're inspecting after you clean, that verifies everything is ready to go and you can mate your two ferrules together. Connector cleaning should be relatively simple. All you need is some alcohol. These cleaning sticks down here, the CS125 and the CS-250 work really well. You just take the cap off, stick it in there. It does a wipe of the end face of the ferrule and cleans all that debris and takes it out. Rather than just mushing it around in there and getting it to spread around on the fiber end face, it'll actually get in there and clean it and remove it by spinning and it's kind of like a dental floss, but it kind of spins over the end of the tip of the cleaning device, and also rotates around in like 360 degrees. So it's spinning and advancing all at the same time, which basically causes a wiping action away and removes that dirt and debris from the ferrule. So make sure you're doing that regardless of what OTDR you go with at the end of your decision. So final thoughts. We've gone about over an hour now. So final thoughts. Definitely recommend a link view software. It has its advantages, but definitely make sure that you keep the raw trace file around as well, because it's a great add-on to the raw trace file. But a lot of times to troubleshoot something, you really need to be able to see the trace file, so having access to that is definitely a requirement. Go with a company who can provide a U.S.-based warranty. As the products overseas, typically we're getting high failure rates, issues, warranties, things of that nature. All about you guys finding the right price point and getting the most competitive price, but definitely would recommend going with a U.S. Company that can warranty it and provide the service that you need. Always use a launch box or pulse suppressor, so make sure you're getting a quote on those whenever you're getting a quote on your products. And then if you need any assistance with generation of trace reports or things of that nature, that's another thing to kind of consider is who's going to be doing that trace analysis. It's one of the things that we offer as a company. Well, people send trace files to us, clean them up, and do bidirectional analysis. But if you're going to request that a partner do that type of service for you, make sure that you're picking a platform that has a SOR type of file format that it can be exported to, because that's kind of the universal standard out there. Otherwise, you might have some sort of compatibility issues that may arise. So those are the final thoughts I had for you. I really appreciate your time today. It's been a pleasure to go through some of this with you. Hopefully I was clear on most of my points, and if you have any other questions, feel free to email us at sales@fiberoptic.com. I'm more than happy to take any questions that you may have directly, and I would love to be able to point you in the right direction and make sure you're comfortable with your end purchase. Thanks so much. Have a great day. Looking for any questions, so we'll open it up and see what we have here. Don't see any questions coming in. I'll wait just a few minutes if there is, otherwise we'll wrap it up. Okay, well, it looks like I was